Good evening. I'm Stewart Brand from the Long Now Foundation. I could do the whole hour on Kevin Kelly. It would be an interesting one to do, actually. He's done a few unusual things. He's biked across America twice. He's walked the Appalachian Trail, most of it. Says it's pretty boring. He spent 10 years, instead of being in college, which he dropped out in his freshman year, walking all over Southeast Asia and taking photographs, astonishingly all of which survived that, and he put out in a book called Asia Grace, which is just photographs, no captions. But there is a link to the web, and you go to the web, and that's where you find out about what's going on in the pictures. That's normal for Kevin. He is always up to something connected but strange. A lot of us who've known and watching him slogging away on this book, What Technology Wants, for years now, have been waiting to see pieces of it, and that's what we're seeing tonight, specifically looking at the history and future of science. Kevin Kelly.
Thank you. It's wonderful to be on the other side of this program. What I want to talk about is something that is very important to us, but we don't talk about very much, which is science. Science produces the only news, but it's really the news itself. I have had a sort of a long interest in science. I began as a kid. I had a nature museum in my basement when I was in junior high school. Then I got a chemistry set, and I think perhaps it was the most unusual chemistry set in America for a boy, because I actually did not make a bomb. I never tried to blow anything up. I actually tried to make nylon once. I was trying to do chromatography. I was actually trying to do cool stuff with chemistry, and from there I went on to high school. I took I think every single science and math class that my high school offered. But as Stewart said a little bit, maybe too prominently, I dropped out of college, found it a little too boring as well, and I went to Asia, where I basically awarded myself an advanced degree in Asian studies. And but all that time, I kept thinking, well, maybe I missed out on science. Maybe I should have really tried science. And so I actually invited myself to a friend who ran a lab, who was a professor at University of Georgia, and he was doing a microbiology lab, and I went down to Georgia and I worked in his lab where we were studying lipids. And I actually made a film with him, and this is, we made an educational film on digestion, and a note about the white lab coats. Scientists do not wear white lab coats, but we were in a film, and the guy who made the film insisted that we wear them. So it turns out that actually I'm a very bad scientist. I don't really have the patience and the dedication that you need to do science. And so while I dropped out, the guy I worked with went on to greater things. He actually was studying lipids and getting proteins across lipids, and then he went on to Genentech as well. And right now, just last month, the FDA approved his inhalable insulin. That was his product. And so now he's changing the lives of many people in the world. But I dropped out, and I did the next best thing, which is that I married a scientist. So my wife, who's here, Jameen, is a scientist at Genentech, and she's a biochemist. And while I'm at home typing up little reviews of the next best bottle opener, she's trying to cure cancer. And she also makes it very she also makes it very clear that my knowledge of molecular biology and genetics is pretty flip-flop, and but I still enjoy hanging around with scientists and talking to them. And so while I was at Athens and researching, one of the things the reason why I did not become a scientist was became much more interested in what scientists were doing. Rather than trying to study what the lipids were, I became really interested in how scientists themselves were processing information. How did they know what to do? How did they get information themselves? How did they pass it around? I became much more interested in the science process rather than the scientific work. And in fact, I became so interested that I actually wrote up a little article. It was one of the first articles that was published, and it was called Information as a Communicable Disease. And not coincidentally, it was published in Stewart Brand's magazine at that time called Coevolution Quarterly. And I was really interested in how information is connected and the connections between scientists and the information that they generate. And this is a citation map from Eugene Garfield, which was just trying to make a map of the connections and the references between scientists. And so what happened was I became really interested in science from once removed. And I'm not a scientist, and I'm not even really a science journalist, really, because I don't even have enough of in-depth knowledge about a certain field to be a science journalist. And so for a long time I tried to figure out what is it that I am, and I finally have decided that I am a science groupie. Okay? I like hanging around scientists. I like to hear them talk shop. I like to talk about their science, and most importantly, I like to talk about science itself. And that's an interesting discussion because you can talk to science and the field work and the kind of work and the results science have, but when you want to talk to scientists about science, they're clueless. They look at you in a big blank. They say, if you ask them about, scientific method has changed, it's not going to be the same in the future, it doesn't quite register. The fact that the way we do science will change. And so this is what I want to talk about, is how the scientific method itself has changed over time and how it will change into the future. And I'm really interested in sort of those long-term trends about science, because I think that is the foundation of our culture, it's the foundation of our society, and we really need to look at that. And I'm interested in it for a couple different reasons. And so I know everyone here would like to know about the next 100 years of science, but before we can do that, we have to kind of figure out what science is. Now, there are a lot of lists out there about the best scientific inventions in the last 2,000 years. And that's the kind of common way people think about science. And one of the lists was asked by John Brockman, and the kind of answers he got was very interesting, because he asked some of the most prominent scientists around the world what were the most important scientific inventions in the last 2,000 years, and you get some very interesting questions. So the future of science, as we think about it, is not this, okay? That's not what the future of science is really about. I want to talk about something else. The kind of example that people would give for the best invention in the last 2,000 years would be something like hay. This is actually Freeman Dyson's suggestion, who was working off of Lynn White and others, who said, well, hay, it was domesticated and made possible the storage of animals over the winters, and that it was basically a part of the agricultural revolution, and that in its way, it furthered the development of our culture more than other things. Another common reply is, well, penicillin or antibiotics. These were obviously things that changed the course of history. Paper. Well, paper was a great invention, right? It allowed printing and then money, and that itself, of course, transformed our economy. The rudder was another example. It allowed navigation, exploration of the seas, it allowed the settlement of Micronesia and Australia, and it was very important in changing the dynamics later on in terms of empires. Or electricity. Of course, that changed the world too. But in each one of these cases, this is not what I'm talking about. I'm not talking about the different little things that science throws off. I'm trying to talk about something else, something more profound. And in some senses, this is like the ideas that the brain throws off. If you're trying to really study the brain, you're not going to just look at the words that people use or the words that people say or the ideas that the brain has. You want to study the dynamics of the brain itself rather than the words that are thrown off. And so if you try to think about the categorizations, if we ask yourself, is there a pattern to all the scientific inventions of the past? The common way that we kind of line them up is to say, well, we have some idea of Stone Age, Bronze Age, iron, steam. We can kind of see them in that way. And again, this is not really, I think, very helpful in trying to understand science. I went back to try to find out the first conceptions of science, when science was first used. And around 1000 in the medieval era, there were 7 sciences, and they were basically types of desk work. They were a type of knowledge, but they were things that were done at a desk. The very first example I could find, and that one of the first examples I could find of the word science, was used often interchangeably with another word called sapiens, science and sapiens. They both meant knowledge. In fact, it's probably only a quirk of language that Linnaeus didn't name us Homo sciens. He could have just as easily, because at that time, in the medieval, before his time, that was what the word meant. It meant knowledge. And it was not until the 1700s that science came to be seen as a word to indicate a process of how we come to knowledge. And it's that word that has taken on its meaning now and that I'm most interested in. So the interesting aspect about what we have when we have a process is that it enables sustainable long-term change. That's what we get from science over time, is we have change that's sustainable over long terms. And it's not at first what we think of as civilization. Because the interesting thing about civilization is that civilizations come and go. Okay? Civilizations disappear. And so we have this sense in which a civilization can come up and have a reign for a while and then they go away. But science is much more of a progressive sensibility. There is something else going on besides just the fact that we have a civilization. In fact, I think the progressive nature we have in civilization comes from the science part of it. Otherwise, in the old days, before there was much science, there was the appearance of civilization as being more cyclic. I have a chart on my wall in my home office, and this is a map of the civilizations over the last 5,000 years, and there's arranged geographically, and you can kind of get a sense that there's really not a large pattern there. So the aspect of science that I find most interesting, that I want to kind of take a few minutes to talk about right now, is the way in which science makes connections. And I think it's the connections and relationships between ideas and between facts and between knowledge that actually gives science its character and its strength. Now, I think the fact that things are connected is very, very important, because it's sort of politically incorrect to say that Columbus discovered America, or that Oscar von Bringe discovered the gorilla in, say, 1902, because those were things that obviously other humans knew about. But in fact, I think there is a way, which is true within science, that those were discoveries. Because what was happening was we were taking some knowledge that was very isolated before, and we were connecting it to all other things that were known. Those acts brought in some information, and it was being tied into and related to everything else that was known. It was no longer isolated. So the information about the gorillas was kept very local, was not tied in, was not referenced, was not checked, was not in any way improved by the rest of the knowledge that the world knew. And that's what science is doing. So what these things create is basically a structure of sustainable changes. And what these connections do is they allow change to happen in a sustainable way. And as I explored this idea of different ways and different connections within science, there was one idea, one necessary connection that I think I have to make clear, one kind of technical idea, and that is this. Okay. This is basically a picture of recursion. This is a recursive thing where it can go, right now it has a sense that it's going smaller and smaller, but you can go the other way. You can think of something that's bigger inside something bigger and bigger. And there are many ways to do recursion. This is another way. This is more interesting because you can't really see the bubble. It kind of flows from one level, flows into the other, and you're not really sure what's going on. And of course, Escher made this very, very famous in his lithographs. And of course, now we're into the territory of Douglas Hofstadter, who spent an entire book kind of reflecting on the different ways in which there's self-reference. This is the Ouroboros, which is the classical simple thing. Is it eating itself? Is it inside the mouth or outside the mouth? And there's other ways you could have self-reference, which is like a fractal, where the larger whole references the smaller parts, that they're identical in all different scales. But here's another way. Even language has a way that's self-reference. This sentence is false. And so there's a sense in which the sentence points back to itself. And I think that pointing back to itself is very, very profound. And it's very profound in science, because what's happening is that in that pointing back to itself, it's referencing an implicit other level that did not exist before. All right, so when the sentence goes back and points to itself, you're taken out of it, and it's moved to another level of meaning. And that's happening in every emergent system that I can really think of. Is what happens is that the circle creates a new level, an outside experience or outside level that did not exist before. And we have the same thing happening in computer programming. Recursion is a very common pattern, and then what gives a robustness and a power to computer programs is the fact that they can do this. This is a map of the metabolic pathways in a cell, and it's nothing but recursion, as well as most genomes, where they have genes turning on other genes that turn on other genes. So you have this sense in which things point back to themselves, and this pointing back creates another level of existence or reference that did not exist before. This is citation. This is science, where you have authors citing other authors who are citing other authors. You have this sort of web of citations and interconnection of facts, and that is what science generates. It generates paradox, for one thing. These are paradoxical systems because you don't know what's at the bottom when things are kind of turning around to themselves. There's a sense of emergence, a new reference coming out. They're sustainable in the sense that they keep things going. They keep going things around and around. And it's about changeability. Here is a wonderful instance of recursion, which is the US Constitution. Article 5 talks about how you amend the Constitution. So within itself is something that points back to the document itself, and so you have a mechanism for how this is going to change. And that is actually, I think, the power of this document, is that it allows sustainable change over time because it has rules for how it changes itself. It's pointing back to itself. That changeability, that pointing back to itself, it's a little game. It kind of sounds fun, it sounds trivial, but in fact, I think it's actually the engine for making this infinite game, because it can keep going. As long as you're going back to it, you can as long as you're changing the rules that change the change, you can keep the system going forever. So this recursive game can be read in many different ways. You can say, well, science is the evolution of evolution itself, how evolution evolves over time. It's exploring the ways to explore. It favors opportunities which create other new opportunities. Or it's how you play the game of playing all games. That's the infinite game. And what's interesting to me is that if you think about the two large systems that play infinite games, there's two of them. One's science and the other is religion. And I'll come back to that later, but I think that that's the background I want to go into, the history, how science has changed over time. So first, I'd like to talk about the origins of science, then I'd like to talk about the future, and then most important to me, I'd like to talk about the meaning of science. So how does science change over time? Well, the first thing is there were observations, facts, and then people began to do this recursive thing. You had a bibliography. You have a document, a book, that basically references other books. And then one of the first indexes to other books is actually very old. The first collections, very, very early, have indexes to them. Then you had catalogs where they listed, the book itself is listed in the list of other books. Libraries with an index is another kind of same theme, where we're actually, this is a imagination, a virtual rendering of what the Library of Alexandria looked like. They were scrolls. So what's happening is we're starting to structure this information more. Collaborative encyclopedia, where you have more than one person, more than one source coming in to write a book collectively, kind of like open source. Controlled experiment came along, and of course Roger Bacon was very instrumental in that, in suggesting the fact that you want to have an experiment that you could change the variable. So here is, again, another structuring of the information. The laboratories became common, where people decided to actually do things in a controlled setting, again, to structure the information coming out of it. Telescopes, scopes, other things that were invented to allow more data to come in, to generate new data in new ways. By having new tools, you can see new things, have new questions. This was another important advance in the history of science. The Society of Experts, where again, a collective people would try and work on similar kinds of questions and problems and exchange the information between them. So we have a further structuring of that information. Then Boyle was the first to propose that the necessity of having a repeatable experiment in his work with cold pumps and heat and cold. He was saying you have to be able to repeat an experiment in order to make it valid. So they were adding another level of information and structure. Scholarly journals came out along the way, and they started to pass this information and put it into documents, and peer review, which started off as letters being passed between each other, where they were actually starting to evaluate and to check and comment on the work of others in a more organized fashion. And then the hypothesis and prediction, which came with Newton, trying to suggest, well, if this is true, then we should expect this. Again, a further structuring of this. So all these kinds of things I want to show in a diagrammatical way. These notions have no real meaning, but we have a facts. We have lots of facts. We start to add a bibliography around them, which takes the same thing. So one of the items is itself referring to others. That's a bibliography. We have a library that does the same thing. We begin to add other facts outside. We start to have new ways of seeing, new inputs, scopes, telescopes, which bring in more information, which is then connected with hypotheses and predictions, which evaluate. We have another one, it's repeatability. We try it again over here. We add Society of Experts, which are cross-referencing. All these things are to show you that what we have with science is information that's being further and further structured and organized. More into this century, or last century, we have the invention of the falsifiable testability, saying that something really cannot be declared. You can't really judge something unless there's some way to falsify it. That was Popper. And then the randomized design, which is that one of the ways that you want to verify and add depth to the kind of information you're doing is this was Fisher, who said you have to be careful of and be mindful of probability and statistics, that this is an important component. In fact, you can actually do things where you take random or statistical approaches to information. And then the controlled placebo, the idea of that you would actually have basically a null set. You would have 0 in an experiment, and that would be the control. That it was a way, again, of adding structure to it. Computer simulations came along. This was a very big thing. And then the double-blind refinement of an experiment, where you actually, the experimenter and the patient would also both be ignorant of it. Again, different ways in which this information was being structured. And finally, science itself. Not that late, but this was a representation of it, the famous book, The Structure of Scientific Revolutions, suggesting that science itself was a subject of study. And that looks like this. Okay, there's recursion, where you're taking the whole mass of things and then you're looking at it itself. Okay? So my conclusion about all this is that science is a way, it's a process of changing how we know. It's about knowledge, it's about sapience, it's about knowing, and it's a process for changing how we know things. Okay, so that's really interesting, but I think what most everybody really wants to know is, what's the next 1,000 years of science, okay? I mean, so one easy general answer is, well, it's this. Okay, it's more structuring of information, more connections between things that we've made and know, more ways of knowing, deeper, more complex things. But what you really want to know is, well, when are we going to have flying cars? Right? Or robots that talk, or maybe virtual reality. So let me tell you about what some of my speculations are on the next 100 years of science. So first, I would say is that science is going to change more in the next 50 years than it has in the past 400 years. As different as the scientific method is now from it was 400 years ago in Bacon and Boyle and Newton, it's going to be even more different in the next 50 years to 100 years. Okay? Because we're going to continue to restructure how we know about things and the process of how we change how we know. Okay, so the second thing I would say is that it's going to be a bio-century. And it's not just because John Mean's a biologist. It's because biology, even this year, already, is the biggest science that we have. Biology gets the most funding, it has the most scientists working at it, it has the most results being published, it has the most economic value, it's the most ethically and culturally important, and I think it has the most to learn from. Okay, I think there's actually more information in biology for us to extract out of than there is in physics. Okay, so the difference is that while physics is very deep, it hasn't been changing over 4 billion years. It's exactly the same physics as it was from the beginning of time until now. Whereas biology has had 4 billion years of investing huge amount of energy into making it very, very complex and full of information. It's very informationally dense. And so it's a huge treasure trove of things that we don't know. This third thing I would say is that computers are going to lead to a third way of science. And let me take a few minutes to explain what that means. Traditionally, there was two ways, the two pillars of science was measurement and hypothesis. So you take data and you have ideas about it, and the two would sort of feed and test each other. And in the measurement field, we're going to see more and more data. Okay, right now, there's nothing growing faster on this planet than information. Okay, there was a study that Hal Varian and Peter Lyman did at Berkeley, where they measured the growth of information, the total amount of information in the world, and the information is growing at 66% a year. Okay, that dwarfs any other thing that we can measure in terms of its growth over a very long term, over decades, say. I mean, iPod sales may go up 200,000 or something, or 200% in a year, but that's just very short term. But over decades, the only thing that we can measure that's growing that fast is the intangibles of information. Now, what's interesting about 66%, which I don't have a good explanation for, is that basically is Moore's law. Okay, so right now, information is the fastest growing thing, and so we have data coming off. And if we take the history of data, the different thresholds is that the first thing that came along was precision, more and more precise ways to measure. Then we had new spectrums, new varieties to measure. Then they were from new sources like cameras and other kinds of tools. And we also have a more duration, so we can get data all the time. We can run these longer and longer. Okay? And so in some senses, right now we're filling out the entire globe with sensors. It's getting a body in terms of having ears, sound, and all this data is flowing in, and that's what we're headed towards, is this humongous flow of data. I just threw up a couple of of instances of the growth in data, and I call it zillionics because there's zillions of bits, there's zillions of everything, and dealing with zillions of things is actually difficult. It requires kind of a new set of parameters and perspectives to deal with zillions of stuff, and that's what we're talking about. Also, this is getting eclipsed very fast because I noticed that there was 1 terabyte. Well, I just bought a 1 terabyte hard disk 2 weeks ago, and I've already filled it up. It's with videos, digitizing videos from home movies. So terabytes, we're going very fast. We're headed into another realm with this. The second pillar of classical science with hypothesis, learning, where you were going to try and make a theory. You were going to try and structure something, not just measure it. And that would always work off in tandem with observation. Well, some of the things that are coming along that are in the new science coming down is dealing with matrices of multiple hypotheses. So instead of having a serial one where you have an hypothesis, you try it out, you go along, you entertain multiple ones at the same time. And you actually try to navigate through. And so things could be kind of partially true and partially incorrect. And you kind of go through all the possibilities at once. Another way to do it, another way is you actually kind of what we call the combinatorial sweep, is you go through the possibility space. You explore the all possible arrangements. Before computers, this was impossible, but now we can kind of do this on a mass scale. And this is an example of Stephen Wolfram's going through CA space and looking at all possible CAs as a way to try and understand what the general behavior of CAs were rather than doing one experiment and one at a time. And we use combinatorial search in lots of things. You're going making huge libraries of possibilities, and chemistries or chemicals, new ceramics are found that way, rare earths, pharmacology is large molecules, synthesis and multiple hypotheses operating all at once. Now, the third variety that we haven't had is simulations. That was not until 1946, and this is a big thing. We do huge simulations, and what's interesting about the huge simulations is that they generate huge amounts of data. And the bigger and more complex and the realer and more sophisticated they are, the more data that the simulation itself is generating, not the observation. So we have a move now to where I think that most of the data that we're going to be generating is probably going to be coming from simulations and not from observation. That the simulation data will actually dwarf the real data. Not real data, but the observational data. So these three things, instead of two, now we have a tripod of three different kinds of science. And they're feeding off each other in kind of a new way. So this three, where you have simulation, which will in some cases inspire measurement, and other times the measurements will inspire simulation, or you have a hypothesis and a simulation, the two of them working against each other, where you have a hypothesis and you try it out in simulation, and the simulation informs the hypothesis. So now there's a sort of a triangle with three different ways, three different pillars. And I call this sort of intersection of the three, I call that deep science, because it is a different way of doing science, where what you imagine it plays as an important point is what you measure. So there are I can kind of show you how there's three little patterns where maybe in, say, you take real-time measurement, vast amounts of quantity, it can inform a really deep simulation, which can then go out and inform hypothesis, and those three can be working together. You can do the same thing in the health sciences. Again, where you continuous real-time measurement of body functions can be processed in the simulation of the body itself, which can then go and work with different computer-aided theorems about what's happening. And in environmental science, it's the same thing. We see the same triad of deep science. So this third way of science, which is really being propelled by computers, well, maybe we can think of it this way. Maybe it's this is the third way of science. I'm not sure. Where we have Hal there, but it's a way in which computers are changing. The fourth way I think that science is going to change in the next 100 years is science will again create new ways of knowing. An example of that would be wiki-science. Large scales, numbers of people involved in an experiment. I was talking to editor of a science journal recently, and they were saying they were expecting the first 1,000 author paper to come in this year. Okay, it was at the Hadron Collider in Europe. 1,000 authors. Well, there's nothing, that's just the beginning of very, very large experiments that can be done, and maybe even experiments that aren't finished. They're sort of like a Wikipedia where you continually are adding on to it over time. There is no beginning or end. It's like one of those encyclopedia articles done by many, many people all at once. Another interesting thing is compiled negative results. Negative results are what happens when you try an experiment and it doesn't work. Normally that information is thrown away. There's no reason why it should be thrown away because in fact it's very, very important. But who's going to read it all? Well, if you have algorithmic or you have ways in which you can automate the processing of the negative results, it can become very, very valuable. And two things have happened. One is I discovered there actually is a journal that's publishing negative results, the important ones that they feel are important. And secondly, the new journals in the medical field where negative results are often very critical have decided not to accept papers who did not register and therefore showed that they basically, excuse me, let me say that differently. There's clinical trials, and often the negative results will happen very early on, and a pharmacological company has no reason to report them. But now a medical journal will not allow their final results to be published unless they register and let them know their early results. So this is a way to basically enforce the large-scale, habitual recording and processing of negative results. AI computer proofs, this is Kepler's conjecture, which was around from 1590, I think, about how to pack oranges. It was only recently proved with the aid of it was proved with the aid of a computer, and also the proof of it required a computer to prove it. So no human really understands this sufficiently to be able to prove it or to verify the proof. And I think we'll see more of that as well. Triple-blind emergent trials is the idea that if you take enough data all the time and it's non-invasive enough and you statistically have enough people involved, you can actually retroactively go back and extract out your controls. You can actually do it statistically to say that, so that in this sense, neither the person involved nor the experimenters were aware at the time of the experiment that the experiment was going on. So distributed experiments, this is another idea. Again, this is Paul Allen's distributed telescope, which is the fast, cheap, and out of control idea, which is that lots of little things hooked together, lots of small experiments hooked together, lots of small pieces of equipment, lots of small sensors together can, in aggregate, become very, very powerful. And in the past, these ideas never made sense because the transactional costs were so steep that it really didn't make sense. But now, and again, we have example after example proving how these mob, crowd, hive mind, distributed bits can actually total up to be something very, very important. And I think the same thing will happen with science. And again, the last thing is the return of the subjective, this recursive coming around, which says that science has, for all time, been trying to push out the subjective and remain objective, to distance itself from the subjective experience. But when you get down to the very bottoms of things and the very largest of things, where things get really weird, it's actually necessary to come back to a subjective. And I think that we'll see a return of the subjective in some of the most basic things like quantum effects, that is almost inescapable that not to bring in that recursive loop back into the equation. We don't have very good tools about how to do that scientifically, but I think that's what will involve. So the fifth and last way I think science will change in the next 100 years is that we'll create a new level of meaning. And what do I mean by that? Only this, that if we take this citation map, which I showed before, this is a much deeper one that's showing in the chemical journals all the authors who are referencing other authors. It's their map of influences and how facts are related and tested against each other. That is a very recursive net. And this is actually a map of the internet. This is showing the kind of major trunk lines, and there's, I think Asia is red and North America is blue. It's a pretty current image of the full interconnection and recursive nature of the internet. And I think what's happening is that this is becoming one machine. And I wanted to, and I really treated this seriously as if it was a machine. If you had all the computers in the world hooked up through the internet, and you actually summed up their specs, what would you have? Well, you can read it here. 1 billion PC chips, 1 million emails per second, 1 million IM messages per second, 8 terabyte, blah, 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 blah. So I said, well, that's a very interesting computer. I mean, that's a pretty big computer. And actually, I did some other things, and I figured out, if we were selling this on Amazon, it would be $1 trillion, and you got 1 billion trips, 1 megahertz email. Okay, so that's interesting. And what's interesting about this one computer that we're making is that it's actually approaching the complexity of a brain. So this is other. If you take all the transistors and all the PCs in the whole world connected together, there's a quintillion of them. If you take all the web pages all the ones in the deep web pages, on average they have about 15 links on each page. There's 1 trillion links, which you can see as a synapse, as in a brain. There's 20 petahertz of synapse firings. That's the speed at which the thing fires. And there's 20 exabyte of memory. That's a very big machine. That's approaching the complexity of the human brain. It's about 100. It's about 2 orders off. But the thing about the internet is it's doubling every year, and the brain's not doing that. Okay. So I think, and if we add our own brains at the other end of it, we have a very large machine. And this machine is actually what's doing science now. This new structuring of information and knowledge is the thing that is now doing science. And a lot of people are kind of worried about that because you've heard Ray Kurzweil's suggestion that once this happens, that we'll just take off and the technology will accelerate into a singularity. I think the singularity is actually an illusion. I think that it doesn't happen from. I think that the technology acceleration is valid, but I think the idea that we're going to go through something that will change and it be a discontinuity is not. This is one of my favorite New Yorker cartoons. For those who can't see it in the back, it's the guy is coming in from lunch after a long lunch, and he coming in, and his very perky secretary is waving a little memo sheet and says, "Sir, the following paradigm shifts occurred while you were out." I think that what happens is that we've already been through several of these large-scale lifting up of new levels of meaning, this emergent thing where things come back and they come up, but we didn't even notice it. Here's another cartoon. 2 guys in the cave saying, "Hey, did anyone notice that we're using language?" We never did that because language was a singularity, but we went through it without any noticing it. Just as we'll go through this one machine, this large corpus of the new thing that's doing science. It's an infinite game. We raise up to the new level connects and restructures in such a way that it lifts up to another level. So one of the things I think that science does not do, which is a very common idea, is that it seeks after truth. That's what people say. I've heard this the other day, a famous scientist said that's what science is, always seeking after truth. And actually, I don't think that's true. I think there is a true, and of course, mathematics, it doesn't change, but there are lots of things that we know about science, or we think we know, that is not true over time. Even the idea that the world is round, well, we find out the world's not really perfectly round, it's off, and then maybe in another dimension it's not round. So even facts like that will change over time. So I don't think it's actually what truth is, that what science is really after. There's an interesting thing about discovery and invention, which is that when you have enough choices, when the field is big enough, when there's enough variables, when the degrees of freedom are sufficient, that the distinction between discovery and invention are nil, that they're basically equivalent. It's the same act. We can kind of see that, and it's a picture of some biological forms, and we can say, well, evolution or nature Did they invent those or discover those? But we understand that they were equivalent ideas. So we could say in the same way that Edison discovered the light bulb. He didn't really invent it, he discovered it. Or that Benjamin Franklin invented electricity. We could say that Pythagoras invented the Pythagorean theorem. Okay? So in the same way, that I think the difference between knowing and creating is also equivalent. There's an equivalency in knowing is not passive, as I'm suggesting it. It's a constructive thing. We're constructing knowledge. And knowing is a constructive, creative act. And in that way, the process of changing how we know provides us with possibilities. So I think this is actually what science is about. Science is about possibilities. It's about differences, options, choices, freedoms, diversity. That's what science generates in us. And if we go back to this handy model of the internet and we see all these things here, imagine if this is a space of possibilities of different organisms, all the species on Earth. And this was the possibility space. And what of course, science is trying to do is we're trying to explore and reach all those possibilities. So in some ways, it's infinite ways to play the infinite game. We can go back to the same map of these things, and we can say, well, now imagine if these were actually the different ways in which you could be a person. Imagine if these were a map of the possibility space of all the ways that a person could be born, the various, the introverts are over here, extroverts are kind of, there's a very complex, high-dimension way in which the gifts and talents of different people were mapped. And so what science is in part about is trying to uncover and reach and have us arrive at those places that would provide the knowledge and tools for every person to fulfill their full potential. So I like to imagine what would it be like if Mozart had been born before the piano had been invented, what a loss that would be. Or if you imagine Van Gogh having been born before oil paint was invented, the option of oil paints, or Hitchcock before film. And so I think right now, today, this is my son, Tywin, I think there are children today who are born whose science, whose technology does not exist yet. They're going to live and die without us having provided, collectively, the thing for them. And I think that's a great shame. In some way, I think we have a moral obligation to actually go out and discover and seek and make all those possibilities. And that's so that people can play this infinite game. While I was searching around for the origins of science, I found a very interesting quote. The very, very, very first use of the word science I could find in the English language was in 1340. And it was called, For God of Science is Lord. I'm not sure what it means, but it was interesting that it was being there, because I think I want to come back to the fact that the two entities that we know how to make, the two entities that generate infinite games are science and religion. And I find it interesting that at the bottom of most religions and most beliefs in God or the universe is basically this recursive loop. I mean, you can't get out of it. The beginning of the universe, who made the universe? Well, the universe always was. Or God, who made God? And so you have this sense in which a kind of connecting to itself is the origin of everything, that there is a paradox at the very basis of it. And I think what science is about, for myself, is science is the way we surprise God. That's what we're here for. That's what science is. It's a way for us to surprise God. Now, you might think that's kind of strange, but think about like Second Life. Now, what's cooler? Is it to have a game where you make everything in there, or to have a game where all sufficiently deep enough where the players themselves, these entities, not with people there, but the robots that you make, the bots that you make, are actually going to surprise you as the creator? I mean, which programmer is superior? It's the program where the creation actually completes the creation. And I think that's part of what we have with this idea that we're taking all the possibilities And I think it goes even further than that. Imagine if this is a possibility space of all the possible ways to know. Okay, all the possible ways to know, all the possible ways to be smart, all the possible ways to find out things, all the possible ways to think. So I think it will take all the possible species of intelligence in order for the universe to understand itself. Okay? So the universe cannot understand itself until we have all the possible ways to structure the knowledge. Another way of saying it, the way I would say it, is that it will take all possible minds in the universe to know the mind of God. And so, for that reason, I think science is holy. I think it's a holy act. I think it's a holy work. And I think that the long-term future of science is actually a divine trip. Thank you. I welcome questions.
Divine Rights trip lives. I'm slow getting up here because I was scribbling notes as fast as I possibly could. Question from Saul Griffith. Where are you, Saul? Somewhere out there.
There
he is, okay. Will we still need hypothesis if we have sufficiently granular observation and post-observation analysis?
Interesting question. I can't imagine us not having a hypothesis. I think that would be the problem, is we may not need it, but we would have them. And the other interesting thing about science, my observing of scientists, is that there's two types. There are some scientists who work from data first. And there are a lot of scientists who do what you're not supposed to do, which is they have a theory first, and then they go look for data to fill it. That's not supposed to happen, but that happens a lot, and it's actually very fruitful. So I think that even though we don't need it, for many people, they'll find that it's actually a useful way to work.
Not many on history, but here's a good one. 100 years ago, in 1906, this is from Ken. Where's Ken? Wave your hand. Back right up there. In 1906, what was expected then from the next 100 years of science?
I don't know. I don't know. That would be a great question to get a view of the future from 1906. Flying cars, jetpacks, anti-gravity. But the interesting thing about the expectations of science is that there's two sets of inventions. There's a set of inventions that were predicted, and then there was a set of inventions that were not. And I actually had some discussions with Danny Hillis about this. I think the ones that were predicted are ones that we could easily visually see in our mind. Things like X-rays and atomic fusion were not, because it was very hard to visualize. So I think that maybe my second thought answer to your question might be that in 1906 there were probably things that were easy to see in our mind, the picture.
That would be an interesting list, by the way, that we have in your book, is the sort of foreseeable and non-foreseeable discoveries and inventions. Scott Bergquist has a question right over here. Where does the competitiveness of warfare, the laboratory of the battlefield, fit into your view of the progression of science? There's the science of war, you have steel, canned food, mass production,
It's a major funder of it, I would say. I think, even now in the U.S., a lot of interesting work is done through the excuse that it's military related. Other than that, I think people piggyback off of it, and maybe scientists are sometimes not as truthful or as brave in refusing it because it's oftentimes a way to get money. The people banking on the fear of militarism, and they'll say, well, I can at least fund my work, and that does happen a lot.
What if peace breaks out and we have a peaceful century? Does science slow down?
That's a good question. I would hope not, but I don't know. That's a good question. I don't know.
Well, in a sense, this raises, you're putting recursiveness as the core issue with science. And with the net, society or civilization itself is increasingly recursive.
Right.
And so are we now reaching a point where recursion is potentially replacing competitiveness as what could drive science, and so we don't need war, or we don't need even commercial competition to make it go forward?
I actually believe that we actually can live without war, that we can actually have a warless planet. I mean, I really do believe that. And I'm not a pacifist, I'm a policifist.
A what?
A policifist. I believe in police and the rule of law. It's interesting that the only pacifists that we know were pacifists. Pacifism can only happen in cultures where there's the rule of law. Jesus was in the Romans, Gandhi was in the British, Thoreau and Martin Luther King were in the U.S. There were no pacifists in the Mongols. There's no such thing as a Mongolian pacifist at that time. So, not for long. Right. So, I didn't mean to go off on that rant, but...
No, keep going. It's actually when you do the second, third, fourth answer that we get into the really interesting space. Kirk Stoddard, where are you? Way in back. What is the current status and near-term prospects of the All Species Project? Is progress still occurring in small-scale projects, and who is the current point of contact?
The All Species Project, for those who don't know, was a campaign to find, discover, name, catalog every living species on Earth in 25 years. To give you a scale of that challenge, we don't even know how many species we don't know about. So the estimates of how many total species on Earth range between 5 to 30 to 1 million species, depending on how you want to count bacterium. And we do know, well, in fact, we don't even know how many we know. The numbers of species that are known ranges between 1.6, 1.7, and a lot of them are duplicates. So it was a big project. We didn't get very far. We were hoping to have some of the money from individuals, which did not happen. However, the most recent stirrings I hear are from Google, where this seems to be a kind of a perfect Google project in terms of making a big database that has huge numbers of information. And we'll see if anything happens there. But right now, it's stuck in the water, although Craig Venter, who finished the genome, has now gone on to try and do the genomes of bacterium in the sea, and that's actually probably a much better way to try to identify things. And he's actually doing a straight ahead, just go and do it. So there is some work being done in trying to just massively take everything that you can scoop up and try to identify it with DNA.
An update on Craig Venter. I talked to him last week at the TED conference, and sort of, hey, Craig, what are you doing next? Because he's always got some next thing, create life or whatever. Currently, he is looking for potentially extraplanetary organisms at the edge of space, and doing the same kind of shotgun sequencing way out at the outside of the stratosphere as he's been doing out in the middle of the oceans.
Great.
And depending on what turns up there, you may get a sense of everything is earthly or maybe not.
What's your bet?
Sorry?
What's your bet?
Well, my bet is, well, remember there's an actual long bet on the subject of where life not from the Earth will be discovered. And Freeman Dyson bet $1,000 that it would be discovered somewhere then on the surface of another planet. If it's discovered in our outer atmosphere.
Does that count?
He will win that bet, I think, yeah. I wouldn't be surprised either way. Possibility space is big there. Someone with a name from the future named Karthik, who's actually time traveling, says, how do you think language is indebted to science? I feel that a lack, or is limiting on science. I feel the lack of a single language hinders the development of science. Many people's ideas are lost due to the lack of expressing it in a way that everybody else can understand.
I do know from hanging around, from being a science groupie, that scientists are really horrible communicators. So I could see that becoming a problem. I'm I did a recent study of the language on the web and was shocked to find out that 1/3 of the web pages are not in English. It was, and 2/3 of the people are not native English speakers. Most of the Chinese, of course, are just overwhelming the web like anything else. And so I think the prospects of a single language that everybody speaks, maybe English, but it'll be the second language for most people. And then I also believe that machine translation at some point or other will really facilitate the language issue in terms of different languages, if that's what the person meant. If it means just communication, that's always a problem for scientists.
So pretty soon, I would expect, based on what you've been saying already, not only will we get machine translation, but machine improvement. So not only will it translate what was said, but it'll make it better than it was originally said. I want that on my machine. And this relates to a question from Unnamed. Do you think science has failed to explain itself to the greater public, and is this why the theory of evolution is receiving less respect now? And while you're at it, what do you think about, quote, intelligent design? As a Christian.
Yeah, I'll mention something about intelligent design. One thing is I think that in a kind of curious way, I think the intelligent design movement, I'm hopeful that the intelligent design movement will have more effect on the fundamentalists than on anyone else. And that is that it's a step in the right direction. So if the Christians will accept intelligent design, then it's an easier step. And I think, in fact, that in the long term, this will not be an issue, that it's just simply going to go away. This is my feeling. I think this is a little bit like contraception and the Catholics. There was everyone thought that all the Catholics were obeying what the Pope said, but in real life they weren't. And it's actually very similar, I think, even in evangelical circles. People privately believe in evolution, but just go along with it and aren't following even what's being said from the pulpit.
I think there's some data on that. Research was done in the last year or so comparing high school classes where evolution was taught straight versus where evolution was taught teach the controversy, where both evolution and intelligent design were undertaken. And to my astonishment as a biologist, the teach the controversy one worked out better in this sense, that in both cases, the people who thought evolution was what was happening got evolution. Nobody was, didn't get Darwin. But in the case where the controversy was taught, the fundamentalists or the people who had doubts about evolution came out of the class with belief in it.
Yeah.
And you can imagine it was way more fun to talk about in class. And that evolution was not a given. It's probably a good way to teach all kinds of science. That would be interesting. Reinvent science teaching it's all controversial. Okay, here's a question representing a lot of questions. This one version happens to be from Matthew Deans, way over there, I think. Or is that someone scratching their head? When will we see the first zero author paper? In other words, when the network and computers and wikiscience and all that stuff basically is authoring things on their own and the citation just fails.
Yeah, it's when? Well, this is all timing, and I think that I think we will, but I don't have any idea when. Maybe others here who are working on it might know, but I don't. It's a great idea. Zero authors. Good.
Steve Wohlraub. How is scientific progress possible without a sustainable civilization? Say at this point where we're basically down to one variegated but pretty much overlapping civilization.
I think it's not really possible because, I think you would have a very primitive science. You'd have to retreat to something very elementary, and you would lose the depth. I mean, basically, the infrastructure that we have for science right now is phenomenal, and it's not just, of course, scientists. It's the communication pathways. It's it's life support. It's vast underpinning, and so I think it would be really very tough for science as we have now evolved it to continue. I think my point is that there are very different kinds of science, just as there are different kinds of evolution. People don't realize that, people think there's only evolution, but evolution itself has evolved. And so in the beginning of life, evolution was very different than it is now. There's horizontal gene transfer, which is very different than what goes on right now. And so,
well, we're doing horizontal gene
we're
transfer.
going to, in fact, Freeman Dyson calls it the Darwinian interlude, where there was massive horizontal gene transfer long ago, and then there was this couple billion years of non-horizontal, and now we're going to go back to horizontal gene transfer on a massive scale as we swap genes and everything under the sun.
Dan Simon asks, is science moving too fast for the long now? If so, how can it be slowed down? And by the way, should it be slowed down?
Right. I don't think so. I think the speed, I think what happens is we are going to change. I think we, ourselves, our concept of ourselves, our bodies, and again, I think, as I'm suggesting, that science is not being done just by humans, it's being done by this machine. It can operate at a level that's not even our level. And so I don't think science is slowing down. And I think, of course, this is subsumption architecture in the sense that we continue to do our thing, and you have multiple levels. Things operate in multiple scales and multiple speeds. And so I think the new speed will be added on to the current speed, but I don't see it slowing down at all.
So this relates to a question from Philip Phillips, obviously a fictional name. Smoked you out. Is science really unidirectional in its expansion, or can this be reversed by the forces of religion and politics?
Could you say that again? I didn't hear you.
Is science really unidirectional in its expansion? That is, does it always expand, or can it be driven back by basically legislated fear or whatever?
You know, I mean, I take a parallel view of science that I do of life. And what's interesting about life is that, as far as I know, it has never retreated from wherever it's gone. There are certain species of life that obviously have gone extinct. But once life infiltrates any environment at all, it never leaves. I mean, life is down in the rocks, inside the earth. Ask a hospital. A hospital tries to sterilize. They cannot sterilize a room, really. So I think the same thing with science. I think there will be species of science, certain methods, certain varieties of science that may retreat. But I think overall, it's a very progressive force that does not retreat as long as the whole thing is going.
Please clarify how you distinguish between the future of science and the future of technology.
That's a good question. I think science is a sort of a way of thinking, and then the technology is sort of like this fruiting body. It's kind of made real. It's a thought made concrete, in a sense of having not necessarily a mass, but it's something that has boundaries. And so I think there's a very blurred overlap between science and technology as our technology becomes more intangible. So I think the distinction is something that is starting to blur, and it was maybe over time we won't have the same distinction. Science is a process of how things change and how we change our knowing, and I think technology, for now, right now, is something that it throws off. It's like science is sort of like a brain, and then the technology is like the ideas that it has. But of course, science itself can be ideas. So I think there is a distinction, but I think over time they'll become less.
How much is, while we're on it, science itself technology driven?
Well, I think everything, I think science, the tools of science, the tools of science allow new questions, allow new data. So I think it's very, very technology driven. That I think you can make more difference in science by inventing a really great new tool than a great new theory.
What isn't science, asks Eric Lloyd.
What isn't science, what?
What is not science?
What is not science? Religion?
You were getting, kind of converging toward the end there. What's the great distinction between science and religion?
I think that, and I think religion has more of a sense of values for humans in terms of what choices you want to make. And I think science has less of that. I think science is less about humans and more about the general drift of evolution throughout the universe. And in other words, I don't think science cares very much about humans. I don't think it's a human-oriented endeavor, actually.
And how does religion care about humans?
I think religion is what humans care about in a certain sense. In the sense of it's about our relationship to the universe. It's a method for understanding where we fit into the universe.
As knowledge is expanded, it takes each young person a longer time to learn it, or even learn to navigate it. Will this limit future generations' ability to contribute new science?
Well, the solution so far has been you specialize into small, so you know more and more about less and less, which sort of evens things out. No, I think that's what happens. I think that we are basically science is about expanding ignorance. It goes back to my idea that science is not about truth. What happens is that a really good question in science will unleash 20 or 30 other new questions. And so if you're really doing science well, you're expanding the field of what you don't know. In fact, the field of what you don't know is expanding faster than what you are learning. And so I think the speed at which this happens in the lifetime doesn't really make much difference, that there's still plenty to occupy a person, and that you don't have to know the entire field to make great progress. You can pick something that's very, very particular.
What do you think of Jim Lovelock's idea of noticing that more and more of the science literature is more and more about less and less, and
right.
infinite specialization that goes on? And there's no manual of sort of starting over. Suppose a great big pandemic and everything shuts down and then wants to start up again after a period of time. People looking at the kind of papers that you've been citing here will not have the faintest idea what that's about.
Right.
Should there be a compendium, maybe a Wikipedia-like compendium, of basically all science, starting with how to make a fire?
Yep. Yeah, actually I proposed something called the Forever Book. The Forever Book is a book, when you open up, that tells you exactly how to make that book. Okay, so it tells you how to make ink, how to make paper, how to print, and so it gives you the entire recipe to make that book. So it's a forever book because anybody picks it up can make another one just like it. And I think you could have the same thing with a kind of a forever library, where the library told you how to make the form of the library that was in, and you could have you could think of these as seeds for civilization. So you could have various kinds of seeds. You could have a seed that would require a certain environment in order for it to be reconstituted. So I think it's a great idea and an exercise to imagine the different ways in which you could kind of basically compact or reduce the essentials and have it so that it unpacks in a viable way, depending on the emergency. So there'd be one emergency if all life goes off, and another one if you want to go to Mars, where you don't have the biology to depend on. Another one if there's a dark age of some sort, and each of these would have a different kind of a seed that would that you could rebuild from.
That sounds like a long now project.
Yes, let's do that.
Let's do that. Beware, this is how all of the things we do, 10,000-year clocks and stuff came about. Hey, why not? Jen Leach asks what is going to be the last question. You say science is not trying to find truth. How would you define truth? And does it exist?
Actually, I mean, what I was trying to suggest is I think that we actually construct truth, that it is a construction. That in fact, that Ben Franklin actually in a certain way did invent electricity, and that Pythagoras did invent the theorem, and that there's a philosopher, I think his name is Brian Cantwell Smith, who said the electron always existed from the time of Rutherford. And I think actually what we know as truth is basically a convergence of many different connections that we seem to, that buoys us up. That's actually something we construct. And do atoms exist? Do I think atoms exist? Yes. I mean, but my evidence for that is so abstract, is dependent on so many other connections that I would say, yes, it's true that atoms exist, but I have to rest on a very large network of other things to support that. And so my sense of what's true is in a way constructed.
So is it the case if Rutherford had discovered what he discovered but not told anybody, the electron wouldn't have existed until somebody else told
Right,
somebody?
I think so. I think it does not exist until, it does not always exist. It does not always exist until it's actually becomes something that other people agree on.
Truth is an agreement.
I think it's less an agreement and more something that's a construction. I think it's something that, I think we do, in a certain sense, make what we think is real.
Well,
Yeah, exactly.
as one of the questions ended, great lecture.
Thank
Thanks.
you. Thank you.